Let's start again. So a block of mass 1.5 kilograms slides down from rest down a ramp of length 2 meters. Guys, we're just saying that this one can be answered either by using conservation of energy, so from third year, or by F equals ma. The initial height is 0.75 meters above the bottom of the ramp, and the final speed of the block at the bottom was 1.3 meters per second. Calculate the average force of friction acting on the block. So for this one, what we want to do is we want to find the potential energy at the start, at the top, kinetic energy at the bottom. There'll be a difference because there's friction. So that difference in energy will be the work done by friction. And then you use work done to find equals force times distance to find the force of friction. So this is stuff that more of a slightly more complicated part of the third year physics, but it is third year physics. Okay, so first of all, AP at the top is mgh. So mass times gravitational field strength times by the height. Remember, the height is the vertical height, so it's times by 0.75, which comes to 11.025 joules. Okay, I wouldn't round it just yet because you're going to be then using it further on in the question. Kinetic energy at the bottom. Half mv squared. So half times 1.5, and the speed at the bottom of the ramp is 1.3, so 1.3 squared. Don't forget your squared. And that comes to 1.268 joules. So we've got obviously more energy at the top than we have at the bottom, quite a lot more energy. So the energy lost is the difference between them, which comes to 9.76 joules. That's not the answer to the question though, because we're asked to calculate the average force of friction acting on the block. So we want to say the energy lost is equal to the work done due to friction. So work done is force. You can say force times distance, or you probably see in the equation list it is labelled force times S for displacement. So the work done, 9.76, is the force of friction times by the distance travelled by the block, so that's the length of the ramp, so 2.0. So the force of friction comes to 4.9 newtons. If it's all within one question, just round at the end. If it was like part A, find the potential energy at the top, then you'd round potential energy, but because it's all in one, you just round at the end. So that's relatively straightforward stuff that you've seen before a number of times. The second method is using a block going down a slope, so you have to find the component of weight parallel to the slope, so like what we were doing yesterday. So I'll leave that up for a little bit because I think some people are still writing. Okay, so the second part of this is using Newton's law. So we're going to be using F equals ma again. So what I've done is I've just drawn out what we've got again, and I've just added in the component of weight down the slope and any frictional force there as well, which is what we want to find. I've also drawn at the side here a triangle with the measurements on, because what we need to do to find the component of weight down the slope, because we know that WS equals mg sine theta, that we need that angle. So to find that angle, we can just use trigonometry. So sine of alpha is going to be opposite over hypotenuse. So sine of alpha will be the opposite, which is 0.75, divided by the hypotenuse, which is 2.0. So alpha
is going to be inverse sine of 0.25 divided by 2, which is 22 degrees. So we have got 22 degrees there. So then we can find the component of weight down the slope by putting in our numbers. So m, the mass is 1.5. G is 9.8, obviously, because we're on Earth, times sine of 22. So that comes to 5.5 newtons. So we've got this situation here. So we've got 5.5 newtons down the slope. Frictional force is what we want to find. It's 1.5 kilograms, but we still don't know the acceleration. So to find the acceleration, we'll need to use SUVAT. So there's quite a lot to this question. So we know that the distance travelled down the slope is 2 meters. The initial speed, because it's dropped from rest, is 0. Final speed, we're told in the question, is 1.3. And acceleration is what we want to find, and we don't know anything about time. So we'll have to use v squared equals u squared plus 2as. So 1.3 squared equals 0 plus 2 times the acceleration, which is what we want to find, times by 2. So the acceleration comes to 0.42 meters per second squared. Then we can use that in our F equals ma. So it's going to be 5.5 minus the frictional force equals 1.5 times by 0.42. So frictional force will be 5.5 minus 1.5 times 0.42, which comes to 4.87 newtons.
Right, so example 19. A car of mass 800 kilograms travels up a hill at a constant speed of 10 meters per second. The friction on the car is 100 newtons throughout the climb. First of all, calculate the amount of energy supplied by the car's engine to get the car to the top of the hill. So, that engine is going to have to supply energy for it to go up the hill. So it's going to have to supply the potential energy required for it to climb up the hill. But it's also going to have to supply energy to overcome the frictional force. Okay, so the total energy supplied is going to be the potential energy to take it up the hill plus the work done against friction. So mgh plus force times distance, F times S. So it's 800 times 9.8. Remember, it's the vertical height, so 25, plus the force of friction, which is 100, times by the distance travelled, which is 500. And that comes to 246,000 joules. Part B says find the power of the car's engine. So power is energy over time. We've got the energy, we don't have the time. We do, so what we do know is it's travelling at a constant speed of 10 meters per second. And we also know that it has travelled 500 meters. So the time is going to be the distance divided by the speed, yeah. So you'll see there's a few sort of like tricksy parts to these questions where it's not always obvious how to do it. So, but you will be able to do it. There is enough information in the question. It's just you've got to go through a few more steps. So 500 divided by 10, so 50 seconds. So the power is the energy divided by the time, which should come to 4,900 watts. Yeah, I just rounded it. Yeah, 4,920 is fine. Okay, have a read through the next question, the last question in the booklet. Are you okay, Rona? Oh. There you go. Right, the last question should look familiar because it is sort of the diagram from one of the earlier questions that we had gone through. So, am I okay to move on? So we've got a man pulls a garden roller of mass 100 kilograms with a force of 200 newtons acting 30 degrees to the horizontal. So remember, we had this guy pulling it before and we had to work out what the horizontal component was. There's a frictional force of 100 newtons between the roller and the ground. But this time, we want to calculate the work done by the pulling force if the roller moves through a horizontal distance of 5 meters, and then the work done by the frictional force when the roller moves through that distance. So the first thing to do is we're looking at horizontal distances, so we need to find the horizontal component of the force. So we've got our 200, we want to find this one, Fx, and it's 30 degrees. So cos 30 is adjacent over hypotenuse, so Fx over 200. So the x, the horizontal component, is going to be 200 cos 30. Remember the cheat way that I did tell you about, if you want to use it, you don't have to, is that 200 has gone through the 30 to get to Fx, so 200 cos is through. You can completely ignore that though if you want to. So part A, so the horizontal pulling force, we want to know the work done by the pulling force if the roller moves through a horizontal distance of 5 meters. To find the work done by the pulling force, so I'll just put an arrow there because it means it's pulling it in that direction. Force times distance. But we have to use the horizontal component of the force. So 200 cos 30 times by the distance of 5 meters. The reason I don't work it out beforehand is just because it's just easier to write down rather than something point something. So you put that into your calculator, you come out with 866 joules. Oh, have I done something wrong? But sorry, what did you get? You got 300. Are you in the right mode of calculator? No, yeah, not this case, yeah. Okay. B, this is where you're probably, yeah, you went too far ahead. So B, the work done by friction when the roller moves through this distance. So we're looking at the friction separately. So I'm going to put an arrow back the way. Is the force of friction times by the distance moved. So that will be, the friction was 100, wasn't it? So 100 times 5. So 500 joules. And hence calculate the speed of the roller when it's been moved through this distance. So basically what we want to know is what is the kinetic energy gained. Okay, so he's pulling it forward and he's giving it energy of 866. However, there's also it's having to expend energy of 500 joules. So the outcome energy, the energy that then goes towards kinetic energy, is going to be the pulling energy take away the energy against friction. Okay, so the kinetic energy gained is the work done by the pulling force take away the work done against friction. So 866 take away 500, and that's where you got your 366 from, isn't it? Joules. Okay, but that's not it answers the questions. It asks you to calculate the speed of the roller when it's been moved through this distance. So kinetic energy is half mv squared. So the kinetic energy gains, 366, is half times by the mass of the roller, which is 100, times by the speed squared. So you end up with the speed squared being 7.32 and the speed comes to 2.7 meters per second. Okay, so a lot of repetition of National 5 stuff there, but just expanding a little bit on it.